Welcome to section 1.3 on conditional probability and independence. In section 1.2 on probability theory, we introduced the probability function, any function that satisfies the three axioms, Kolmogorov's axioms, is a probability function. In this section, we will introduce the conditional probability function. If you haven't watched Professor Blitzstein's Stat 110 probability class on YouTube, I highly recommend it. At one point, he calls conditioning to be the soul of statistics. Pretty deep, but it is effective in conveying just how important conditioning as an operation is to anything we do in probability and statistics. So this section is essential, so let's get right to it. And let's start with a definition 132 in the book. So the definition of conditional probability of event A given event B. We'll introduce a new notation here. This will stand for probability of event A given event B. And we will express it as the ratio of two unconditional probabilities, where in the numerator we take the intersection of the two sets, and in the denominator we have the probability of the set that we're conditioning on. So again, we have a conditional probability on the left, and the definition expresses it as the ratio of two unconditional probabilities on the right. So notice that in order for this expression on the right side to make sense, the probability of B, the denominator here, needs to be non-zero. So this, and because probability of any event is greater than or equal to 0, and since we need this denominator to be non-zero, that means that the probability of B has to be strictly greater than 0. Okay, so that's the only requirement here. Okay, let's take a little example and kind of think about what it's telling us. So suppose we had a sample space that consisted of, let's say, 16 outcomes. So these could be numbered 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. And so, suppose that you placed some sort of bet on the fact that when this experiment is run, the outcome that will turn up will be contained in set A, where A consists of 1, 2, or 3. So again, just to remind ourselves how this works, an experiment is to be performed, and we have the sample space for the experiment consisting of these 16 outcomes. The sample space contains all the possible outcomes, right? So one of these 16 will happen. And then when the experiment is actually run, only one outcome will turn up. It might be 11 or 2 or 13. Only one outcome will turn up. If that outcome that turns up happens to be an element of set A, we will say that event A happened. So then you will win on your bet, because you bet that the outcome that will turn up will be 1 or 2 or 3. You win in any of those 3 cases. Now suppose that the experiment is run, so there's already an answer, but it's announced through a speaker, and you couldn't hear exactly which outcome turned up, but you heard that it's in the right side of the sample space. So essentially you heard that the outcome that turned up is in set B, but you couldn't hear exactly which one it is. So I'm just writing here what set B consists of. It's these outcomes. Okay, so now let's think in terms of probabilities. When you placed your initial bet here on the probability of A, you had an unconditional probability. So, and we're taking these 16 outcomes here to be equally likely. So each outcome has a probability of 1 over 16 of occurring. Okay, so you placed your bet on A, and so as we've seen in the last section, we can express this probability here as the number of outcomes, because the outcomes are all equal likely, as the number of outcomes in A in the numerator divided by the number of outcomes in the sample space. And we have 3 in the numerator, right? 1, 2, 3, and we have 16 in the sample space. So that was the initial probability of you winning by placing a bet on A. Now the question is, now that you have heard which outcome actually turned up, you couldn't hear exactly what it was, but you heard that it's an element of B, of set B. Does your does your chance of winning change now that you've heard that the outcome that turned up is in set B? Well, let's take a look. So let's look. Let's use the definition. So in the numerator we have A intersection B, and then the denominator. So in the numerator, probability of A intersection B, in the denominator, probability of B. Okay, so so what is the probability of A intersection B? Well, there's only one element at the intersection of A and B. It's down 3, right? You can see it in both of these sets. Okay, and we said that so 3 is just an elementary outcome, and there are 16 elementary outcomes. We said that they're all equally likely. So the probability of the outcome 3 is 1 over 16. Okay, and what's in the denominator? Probability of B. Well, B contains 8 outcomes, so the probability of B is 8 over 16. Right, and then we can just write here, if we divide two fractions, it's multiplying, right, by the second one flipped, and so we get 1 over 8. But I'll multiply the numerator and the denominator by 2 here, so that's the same as 2 over 16. And the only reason I did that is because I want to compare it to the probability we had at the beginning. So the beginning probability of us winning was 3 over 16. But once we've heard this news that the outcome that turned up is in set B, we have updated our probability of winning to 2 over 16. So the probability of winning went down. So that was not kind of the kind of news that we wanted to hear. But just because probability of winning goes down doesn't mean you can't win, right? There is still one outcome which, if that happens, we do win. And let's say that then the winner is announced, and it is actually 3, and so we win. We went through an emotional roller coaster here. There was a certain probability of winning, 3 over 16. Then we heard this partial information, and it was not encouraging. Our revised probability was lower now, probability of winning. But in the end, we still won. Let's just see a little bit of kind of symmetry that it has about it. So if instead we had the probability of B given event A, well, just using the definition, then it's the probability of B intersection A divided by the probability of A. Right, but you remember from section 2.1 that B intersection A is the same as A intersection B. I think that was the law of commutativity. So then in the numerator we can write it as A intersection B over probability of A. Okay, and then so let's just ignore this intermediate step so it doesn't confuse us. And so notice that we have this numerator here that's the same as this one here. And so what we can do then is we can express this probability of the intersection of A and B two different ways. First, we can use this side here and write it as probability of B times probability of A given B. But alternatively, we can also express it from the right side here as probability of A times probability of B given A. There's a claim on page 21 that for any B, any set B with probability of B being strictly greater than 0, it says that it is straightforward to verify that the probability function P conditional on B satisfies the Kolmogorov's axioms, basically that this is a probability function. And as part of exercise 1.35, we're asked to prove it. I think this is a very key result here, and so I will prove it now. Okay, so in order for us to show that it's a probability function, we'll need to show that the three axioms are satisfied, right? So let's briefly restate the three axioms. So the first one said that the probability of any event A is greater than or equal to 0, and that's true for all events A that are members of the Borel field. The second one said that the probability of the sample space is 1, and the third one said that for pairwise disjoint sets A1, A2, and so forth, pairwise disjoint, the probability of the infinite union of AI is equal to the sum, the infinite sum of the individual probabilities. Okay, so those are the three axioms, and now we want to show that the conditional probability function satisfies these three axioms. So I remember when I first looked at it, the hard part was to understand what these would look like for this conditional probability function. So let's write here to the right what would need to be satisfied for us to say that this conditional function does satisfy the axiom. So what would need to be true for the first one? So if we can show that the probability of any event A conditional on event B here, that has a positive probability, if we can show that this conditional probability is greater than or equal to 0 for all A elements of the Borel field, then we've shown that axiom 1 holds for this conditional probability function. For the second one, we would just need to show that the probability of the sample space given this event B is 1. So notice it's the same thing, all the conditions, but now everything is given B. And then the third one would be that given pairwise disjoint sets A1, A2, and so forth, it is true that the probability of the infinite union of AI conditional on B is equal to the sum, infinite sum, of the individual probabilities, but now conditional on B. Okay, so that looks right. So we want to show that these three conditions in green hold. If they do, we'll say that this conditional probability function, well, that this candidate function here is a probability function. Okay, so let's take them one at a time. So let's work on the first one. So okay, so we want to show that the probability of A conditional on B is greater than or equal to 0. Okay, so let's see how we can unpack this. Well, we can just use the definition of probability of A given B from above. So that's the ratio of two unconditional probabilities. Okay, and what else? Well, actually, I think that if now we adjusted, all we need is a change of perspective because the answer is already looking at us here. And notice that in the denominator, we have a probability that's greater than 0 because we had to assume that. And in the numerator, well, A intersection B is some event. And we know from axiom 1 that the probability of any event is greater than or equal to 0. Right? Because P is a probability function. So then, with the numerator greater than or equal to 0 and the denominator that's strictly positive, we will get something that is greater than or equal to 0. And this will be true for any A elements of the Borel field. Okay, so we are done with this one. Okay, then let's move on to the second one. So we want to show that the probability of the sample space conditional on B is equal to 1. Okay, well, let's apply the definition from above again, what it means, what conditional probability is. So then we need to take the intersection of the sample space and B divided by probability of B. Okay, but what is the intersection of B and sample space? Well, that's just B, right? Anything intersected with the sample space is going to be just that. So that's going to be probability of B over the probability of B, and we get 1. And that is what we needed to show. So then both axiom 1 and 2 are satisfied. Okay, now we need to show that the third one holds as well. So I'll just make some room here. Okay, so we want to show that this here on the left equals this part on the right. So okay, well, so let's start with the expression on the left. So we have that the probability of the infinite union of sets AI conditional on B. So I'll unpack this a little bit because sometimes this infinite notation makes things a little harder to see what's going on. So what we really have here is this, right? A1 union with A2, union with A3, and union and so on. And this is conditional on B. Okay. And okay, so this is a set, some set, right? M. So we have the probability of M given B. So we can use the definition from above here. And we know that now will be the ratio of probability of intersection of M and B over the probability of B. So let's write that out. So I won't write M, but I'll write what it is. It's this chain of unions. Okay. So that's our M and intersection with B over the probability of B. Right? That's what we got there. Okay. Now you may already see the distributive law over there in the numerator, but if you don't, let me just write it slightly different, and then you'll see it in a minute. So here I'm using the commutative law. Remember, it said that. One second, let me write first because I cannot write and think at the same time. It just doesn't work. Okay, so we got this. Okay, so okay, what we had here was probability of M intersected with B, and I rewrote it as the probability of B intersected with M. We can do that by the commutative law, and the reason I think that this is better, because now recall what the distributive law said. Remember, with the distributive law we had probability of a set intersected with a chain of sets held together by the union. So now we're going to distribute an intersection to each set in the parentheses. So we'll have B intersection A1, we'll have B intersection with A2, B intersection with A3, and now these will be held together by the operator operating inside the parentheses, and that's union. Right, so this is what we get in the numerator, and the denominator we still got the probability of B. So if we just look at a sample space for a minute, and let's draw a set B. So B represents all the points inside, and then let's draw some sets AI, which are pairwise disjoint. So let's draw, this is A1, A2, let's draw an A3 here, and an A4. So now let's look at these sets, B intersection with A1. So B intersection with A1 is this part of B, right? B intersection with A2 is this other part of B, which is disjoint with the previous one. B intersection 3, well, there's nothing at the intersection of B and A3, but it is disjoint with the other two sets that we just colored. And B intersection with A4 would be this one. So the point is that all these sets, B intersection with AI, are pairwise disjoint. No two of them have any elements in common. Therefore, what we have here, now let's just see it differently, is the union of infinite union of disjoint sets. And that's exactly what this axiom 3 here, exactly where it applies, right? Because we have disjoint sets, and we're looking at the union of these disjoint sets, and we're told by the axiom that it'll be the sum of the probability of each set. In the denominator we still have probability of B, but in the numerator now we have this summation, goes from 1 to infinity, of the probability of these guys, and that's B intersection with AI. Okay, and now we can erase this part here, and so probability of B is just a scalar, right? So we can bring that under the summation sign. So we can write, so basically we divide each term here in the summation by the probability of B. So then we can write it as probability of B intersection with AI divided by the probability of B. And let's not forget what the destination is here, right? We're trying to get to this right side. We're trying to show that it equals that. And well, recall the definition here. And now we're just going from the right side to the left. And so you see that we can write this as the infinite sum of the probability of AI given B. Okay, so then we've shown that this third axiom is satisfied as well. Okay, so pretty cool and powerful. So anytime we're given a probability function P and a set B that has a positive probability, which really doesn't require much, then the conditional probability is also a legitimate probability function. That means it satisfies the three axioms, and that is going to be very useful. So recall that with unconditional probabilities, it is true that the probability of the complement of A is equal to 1 minus probability of A. We've proven that in section 1.2. Let's explore now the claim that this still holds true if we condition on a set B. So the question is whether this is true. Probability of B strictly greater than 0. Okay, so let's explore that. The axioms here, this axiom 3, right, the meaty one, it only applies when the sets, these AI sets, are pairwise disjoint. Right? No two of them have any elements in common. So let's think about, let's draw a sample space, and set A, represent all the points inside, and then we know that then the complement of A represents all the points outside of A, right? All the points in the sample space that are outside of A. Okay, so A and the complement of A are pairwise disjoint. Okay, so then by definition 3 that applies to the conditional probability function, we could write that the probability of A unioned with the complement of A conditional on B, right? So we want to evaluate this. Well, the axiom 3 here for conditional probability says that this part here on the left, which is what we got written down here, will equal the sum of the individual conditional probabilities. Probability of A conditional on B plus the probability of the complement of A conditional on B. Right? So I just applied now the axiom 3 that pertains to now the conditional function, this P conditional on B, event B. A unioned with the complement of A, that's just the entire sample space. So what we really have here on the left is probability of the sample space given B, but from the second axiom we know that to be 1. So that's 1. And then what do we have here on the right? Well, we'll keep it as is. Sorry. And you see now that if we just, we're trying to show this, right? We're trying to show this. So if we just isolate this to the right side, basically take this one to the left, then we will have shown that it is true. But the key step here was this, getting used to now applying axiom 3 for conditional probability functions. It's the first time that we've done that. Okay, so now let's move on to Bayes' rule. And to do that, we'll recall that we can write the probability of the intersection of two sets in two different ways. We can write it as probability of A times the probability of B given A, or we can write the probability of B first times the probability of A given B. Right, we've seen this before. Now imagine that we're interested in this term on the right. So we want to understand we want to figure out what the probability of A given B is. Then from this second equality here, we can write it as the ratio, where in the numerator we'll have the probability of A times the probability of B given A, and in the denominator the probability of B. So this is Bayes' rule in its simplest form. So there is one more form in which we unpack the denominator, and we'll do that in a second. But let me just mention that we'll come back to looking at Bayes' rule more further in the course when we start interpreting probabilities. So far, notice that we have not interpreted probabilities. We have not given probabilities a frequentist or a Bayesian interpretation. We haven't asked what does it mean for to have a probability of 0.3 or 0.8. The only thing we've talked about is that if we have a function that's a probability function, then the outputs, the numbers generated by that function are legitimate probabilities. And we stopped at that. That's the axiomatic approach. Okay, so let's see that alternative form of Bayes' rule in which we unpack the probability of B. So this other form uses a partition. So it says that if we have a partition, A1, A2, and so forth, a partition of the sample space, well then we've seen a result in, I believe it was theorem 1 to 11. Yes, in 1 to 11, in part A, we have shown that the probability of a set A can be written as the sum, the infinite sum of the probability of A intersection with Ci for any partition C1, C2, C3. So we've seen that result, but let's quickly just kind of remind ourselves why that's true. So suppose that we had this partition here, and I'll just use only a few sets here. So the collection of these 6 sets represents a partition. They're all pairwise disjoint. Their union is the sample space. And then we have a sample, we have a set of interest, B. So this is our set B. Then B intersection with A2 is this chunk. B intersection with A1 is the empty set. B intersection with A3 is this part, right? And so you recall that we've looked at this before. The point is that B intersection with AI gives us pairwise disjoint sets, and their union is B. And then we can write B as the union of all these sets. So the first one is A1 intersection with B, the second one is A2 intersection with B, and so on. So in this case, it goes through A6 intersection with B. And then we can take the probability of both sides, and now on the right side by axiom 3, because these are pairwise disjoint, we can write it as the sum of the probability of each term right. So with summation notation, that's what it would look like, and so that looks good. Okay, and then let's use this definition of the intersection here, and in particular because eventually we're going to be plugging this back into this form of Bayes' rule, and here the probability of A given B is the unknown, is what we're trying to figure out. We will not care about this form, but rather we would prefer this other form. So okay, so then we'll write it as the summation as I goes from 1 to 6 of the probability of A. So it's probability of AI times the probability of B given AI. Okay, and so now let's write this definition properly, this alternative definition of Bayes' rule. I'll make a little bit of room here at the top. So then the probability of any of these sets AI given B will be given by the numerator is same as it was in the other form, probability of AI times the probability of B given AI. But now in the denominator we're going to have this expression here. But notice that we already used the index I, and here at the bottom this I here plays a different role. This one just goes from 1 to 6 and is different from the AI that we have above, so we'll just give this one a different letter. So let's make it a J and change this I to J and this one to a J. Okay, now it's ready to be plugged in there. So we have a sum as J goes from 1 to, and we worked with a partition of 6 sets, but we could have infinitely many of them. So we'll take that case and it'll be a summation of the probability of AJ times the probability of B given AJ. Okay, so this is the second form of Bayes' rule expressed in terms of a partition of the sample space. Okay, so that's it for Bayes' rule. Now let's talk about independence. So if we think about it, there's basically like an event universe, and there's a probability universe. So we're thinking a little more artistically about it now. Okay, so there are these two universes. And if you think about what we've done so far, we have sort of thought of something in the event universe. For example, we may have had a sample space, and we thought, okay, well, if we have a set A that is a subset of set B, we know how to draw those in the event universe. It means A has to be drawn inside of B, okay? But what does that imply about the probabilities of these two sets? And we looked at that and we said, okay, well, in that case, because A is a subset of B, the probability of A, we've shown it that it has to be less than or equal than the probability of B. Okay, and that kind of satisfied our curiosity about the probability universe. And then we took another question, and we asked, okay, let's say that now we're interested in set A and its complement, and so we have these two sets, A and the complement of A, and then we were wondering how their probabilities relate. And so we studied that, and we've shown that the probability of the complement of A is just 1 minus the probability of A. And again, that kind of satisfied our curiosity. And so on and so forth. And so for example, I'll just edit this second one and draw one more. We looked at sets A and B and wondered about the intersection, and and then we've derived an expression about the intersection of probability of A and B. And we've shown that it is equal to the probability of A plus the probability of B minus the probability of A union B. So once again, we pictured two sets in the event universe, and we wondered, and then we conceived of this new set, which is the intersection of these two sets, A and B, and we wondered how then the probabilities of these sets related. And so that's what we explored. So now is the first time, really, the first time that we will make an observation in the probability universe, and we're going to look back to the event universe and infer something about the event universe from an observation in the probability universe. And you can imagine that it must be some pretty special observation that we make here in the probability universe that it gets us to go backwards for the first time. And that observation is the independence of sets. So essentially, we observe that if we have two sets, A and B, such that their intersection, the probability of their intersection, equals the product of the two probabilities, then for whatever reason we are interested in these sets A and B, and we want to start thinking about what they would look like in the event universe. So the first place I want to go here is to answer the question, why would we care about independence? So why is independence so interesting that we're making this reverse journey from the probability universe to the event universe? So to explore that, let's go back to the example we had where we placed a bet, and if you recall, set A consisted of outcomes 1 through 3. So that was our set A. So essentially we placed a bet on this set A, right? And so the story then we had was that set B happened. So there was an announcement, so the experiment happened, and one of these 16 outcomes occurred, but the announcement was made through the speaker where we couldn't exactly hear, but we heard that the outcome that occurred was on the right side of the sample space, so effectively in this set B. And we looked at the fact that the probability of the set A, the unconditional probability, is, well, that's just 3 outcomes out of 16, and the probability of the set A conditional in B, once B became the new sample space, so then these 8 outcomes to the right of the sample space became the new sample space, and in this new sample space there's only one outcome, that's an A. So by the formula, this is probability of A intersection B over the probability of B, and we said there's only one outcome in A intersection B. So to be more precise, in the numerator, the probability of A intersection B would be 1 over 16, and then in the denominator, the probability of B is 8 over 16, and that's 1 over 8. Which we then multiplied by 2, both the numerator and denominator, and got it to be 2 over 16, right? Just so that we can compare it to this 3 over 16. So you recall this exercise, right? So now here's a claim. No matter what event B we pick, the probability of A given B will always be different than the probability of A. So, you know, I was just thinking about it, and yeah, this sounds true, because the probability of A is 3/16. And then, so imagine that, you know, so that the event A is fixed, but the event B, you can vary it over the sample space. So, you know, try picking a set B that would make the probability of A conditional on B equal to the probability of A. There's no such set B. And, you know, we can see that by, you know, just kind of unpacking a little bit what this probability of A given B is. You know, we've shown it here to be the ratio of the probability of the intersection of the probability of B. And you know, so and then we've seen that it's the ratio of what? So this is how many, this one in the top is how many outcomes there are in the intersection in this set A intersection of B, and this 8 here is how many outcomes there are in the set B. So, you know, so effectively we're looking at number of outcomes in A intersection B divided by the number of outcomes in B. So, you know, as you in your mind vary this set B in size and, you know, in position over the sample space, you know, we're looking for this ratio over here, which will give us the probability of A given B, and we want this to equal, you know, if we wanted this to equal probability of A, then we want this to be 3/16. Okay, you know, but you know, imagine that you know, we keep B of set B of size 8 outcomes, you know, then this would be what? It would be, you know, so we would have 8 in the denominator, and then we would need a non-integer number in the numerator to get us this equality with 3/16. And, you know, so we cannot have a non-integer number of outcomes in A intersection B. So that's just kind of a hand-wavy, you know, more intuitive explanation of why there is no set B such that the probability of A given B is equal to the probability of A. So that means then that this, you know, probability, this event B, which is, you know, this announcement over the speaker that you can't hear exactly, it will always change the probability. So we'll start with some probability of A, and then after this announcement is made, no matter what that set B looks like, the probability of A given B after we hear the announcement will be different than our initial probability. So we'll be revising our original probability. Now, independence talks about that rare case when we have equality here. So the independence refers to the rare case when the probability of A given B is actually equal to the probability of A. We've seen that if event A, you know, consists of the 3 outcomes, you know, that we pictured here, that there is no event B which would make A and B independent. But now if we slightly changed the set A to now include the first row, so those 4 outcomes, can we find the set B now such that the probability of A given B would be equal to the probability of A? So in this case, the unconditional probability of A consists of 4 outcomes out of 16. They're all equally likely, so the probability of A is 1 over 4. Okay, and then so as we're thinking of how should we draw B, so that probability of A given B is equal to probability of A, we're thinking about the intersection of A and B, and if we kept B same as it was before, that should work. So let's take a look. So if B becomes the new sample space, the probability of A given B is the probability of the intersection of A and B divided by the probability of B. And the probability of A intersection B now consists of 2 elements. So that's 2 over 16, and the probability of B is 8 over 16, and that's 2 over 8, so that's 1 over 4. Okay, so we have now this equality holding, and in such a case we will say that A and B, the events A and B, are statistically independent. Pretty cool. So that says that this event B that happened didn't change our initial probability of the event A. And it says even more, because if we looked in the other direction, so if we looked at starting with the probability of event B and evaluated this unconditional probability, well, that's 8 over 16, and that's just 1/2. And then if we evaluated what's the probability of B if A happened first and the sample space was updated to A, well, that would be the probability of the intersection of A and B divided by the probability of A. And what's in the intersection of A and B was the same 2 elements, so that's 2 over 16. And what's the probability of A? Well, A consists of 4 elements, so that's 4 over 16, and we get 2 over 4, and that is 1/2. So notice that the probability of B equals the probability of B given A. So we've also shown that the probability of B given A equals the probability of B. So if A and B are statistically independent, then both of these statements are true. Okay, and let's do one last thing here. Let's recall what the probability of A intersection B is. We said that it can be written in 2 forms. Probability of A times probability of B given A, but also as probability of B times probability of A given B. And when A and B are statistically independent, we can replace these expressions in here, and let's see what that implies for the probability of the independence of A and B. So from this first equality, so we get that the probability of A intersection B is equal to the probability of A times, and I'll replace the probability of B given A with the probability of B. Okay, so if A and B are statistically independent, then you see the probability of A intersection B is just the probability of A times probability of B. And from the second one, as you can see, probability of A given B is just probability of A, so effectively we will get probability of B times probability of A. That's not interesting, so no need to write it that way. So we see that this is the point, that if A and B are statistically independent, then the probability of their intersection is equal to the product of their individual probabilities. Okay, so let's go back now to the previous slide. So we've explored now why this observation in the probability universe is interesting. Because when this product holds, that means that A and B are statistically independent, and that means that the occurrence of one of these events does not alter the original probability of the other event. So, okay, so we've seen why we would care about statistical independence. Now let's see if we can, build in our minds any sort of understanding of what A and B, two sets that are statistically or two events that are statistically independent, what would they look like in the event universe? For example, can they look like this? Can this be A and B? So let's explore that. I have drawn here 4 identical sample spaces and 4 identical events A and an event B that has the same unconditional probability, right, the same area in each of these 4 sample spaces, but the position of event B differs, and hence how event B and A interact differs. So here's the question. In which of these 4 sample spaces are A and B statistically independent? So take a moment to think about that. And let's go through each of these. So let's look at the first one. Notice that B and A are disjoint in 1. They do not have any points in common. And notice that the probability of A must be greater than 0 because A is definitely not the empty set. There are points inside there, right? Okay, so probability of A is greater than 0. And let's explore now the probability of A given B. We know from the formula that is the probability of A intersection with B over the probability of B. Okay, so in the numerator we have the probability of A intersection with B. But there's nothing at the intersection of A and B. A intersection B is the empty set. And we have shown that the probability of the empty set is 0. And therefore this must equal 0. And we know that the probability of B is strictly greater than 0 because we can see that yellow circle there and it has points inside. So the point is that we have shown that the probability of A is positive while the probability of A given B is equal to 0. Therefore, we have shown that the probability of A is not equal to the probability of A given B, and that is sufficient for us to conclude that A and B are not statistically independent. And I think that this result is a bit surprising, because if we hear that events A and B are independent, and if we just literally interpret the word independent, we might think that, oh, events A and B have nothing to do with each other. And isn't that what picture 1 kind of shows? They don't have any points in common. But that's not the statistical definition of independence. And so just keep that in mind. Two events that are disjoint are necessarily dependent. That's what we've shown here. A and B are disjoint, they are necessarily dependent. Okay, let's look at now the second scenario. In the second scenario, B is a subset of A. So let's think about what the probability of A given B is. So what does what does it mean to condition on B? Well, it means that B becomes the new sample space, right? So we can call it S new, and this is old. And once B becomes the new sample space, anything outside of B doesn't matter, right? It's just, all that matters now is B. We're focused solely on B, because we know that B now represents the set of potential outcomes. Anything outside of B has a probability of 0. Okay, and given that B is the new sample space, what's the probability of A? Well, A and B are identical here. So essentially we could even write this as a probability of basically the new sample space conditional on the new sample space, and that would be 1. Okay, and we can tell from the way that I've drawn this that I've drawn the rectangle A to take up 1/4 of the area of the entire sample space. So the probability of A is 1/4, and that's definitely not equal to the probability of A given B, which is 1. Therefore, in scenario 2, A and B are also not independent, so they are dependent. Okay, let's take a look at 3. In 3, what do we have here? Well, let's explore what the probability of A given B is. So again, in your minds, think of B now as the new sample space. Anything outside of B does not matter. So when we now zoom in on B, what is the probability of A if B is the new sample space? It's 1/4. I've drawn this very carefully so that the intersection of A and B takes up that second quadrant and is 1/4 of the area of B. Okay, and so you see now that we have found the scenario in which A and B are statistically independent, because probability of A is 1/4, right? The area of A is 1/4 of the sample space, and the probability of A given B is also 1/4. Okay, so we know that this is the correct answer. But let's just take a look at 4, and you see that in 4 it's kind of a similar scenario to 3, but the intersection between A and B is just too tiny. So you can tell that the probability of A given B here is going to be something tiny. Right, once we zoom in on B, nothing outside of it matters. Now it's just a ratio of the intersection, the area of the intersection of A and B to the area of B, and that'll be tiny, so definitely less than 1/4. So we know that the probability of A given B will be different than the probability of A, which means that A and B are not statistically independent, so they are dependent. So we have found the correct answer here, and we've seen that disjoint sets or disjoint events are necessarily dependent. And there's one more observation to be made here, and that is that independence of events is rare. It is the exception rather than the norm. And you can see that by taking the sample space that we have here and keeping event A fixed as we have it, and keep the size of event B the same, and just move it around the sample space. And as you move it to a certain position, think about whether A and B would be independent given the stopping point you found for event B. It would take some exceptional luck to land B in such a position that A and B would be statistically independent. There are very few of those compared to how many there are where A and B are dependent. Okay, let's have a look at Theorem 139. In Theorem 139, we're given that A and B are independent events, and then we're asked to show that some other sets of interest are also independent. So how do we express the fact that A and B are independent events? There are 3 ways we can write that. And let's write it in all 3 ways. The first one is that the probability of the intersection of A and B is equal to the product of the probabilities of the individual sets. That's the first way. Second one is to express what the probability of A conditional B has to be. Well, that has to be equal to the probability of A. And then conversely, we can write that the probability of B given A must equal the probability of B. Okay, so we're given that A and B are statistically independent, so in our minds we have these three identical ways of expressing that fact. Okay, and then we're asked to show in part A that A and the complement of B are also statistically independent. Okay, so let's see. So how do we show that? So what are we trying to show? We're trying to show that these two sets are statistically independent. And see, I'll pick the first form here. So we're trying to show that the product of A intersection with the complement of B is equal, so we want to show that, is equal to the product of probability of A times the probability of the complement of B. Okay, so, you know, as often is the case in problem solving, we want to build a bridge between what we know and what we're trying to show. So we're trying, you know, we're going to try to somehow involve this expression here, the probability of this intersection, and we know this one. And if we've seen these two before, if we draw a sample space, I think we'll be able to recall them. So we have our sets A and B. This here is A intersection B. And then what does A intersection with the complement of B look like? Well, these would be the points that are in A but not in B. So this here is A intersection with the complement of B. Okay, and they are disjoint sets and their union is A. Okay, so that's useful. So we can write that A is equal to the union of these two sets. Let's write the first one, second one, and we want to take their union. By axiom 3, because these are disjoint sets, the probability of their union is equal to the sum of the individual probabilities. So we can write that. Okay, and so again, where are we trying to get here? We want this expression, so let's isolate that to one side. Probability of A intersection with the complement of B is equal to the probability of A minus the probability of A intersection B. But for that we can replace, because A and B are independent, we can replace the expression, this first expression, and here we can factor out the probability of A, and what we have inside is 1 minus the probability of B. Okay, and we have shown that 1 minus the probability of B, that's just the probability of the complement of B. Part B is identical, so I won't cover part B, but part C is different, and so that one is interesting. So in part C, we are asked to show that the complement of A and the complement of B are statistically independent. Well, first of all, let's see. So what are we trying to show? We're trying to show that these two are statistically independent. It means that the probability of their intersection must factor. Okay, so we're trying to show this. Okay, so this is the expression we're interested in, and this is what we got. So let's see if we can build a bridge between those two. So we got our sets A and B, and so we know what A intersection B looks like. This here is A intersection B. And then what about the complement of A intersection with the complement of B? Okay, well those points are the ones that are outside of the union of A and B. Okay, and you see, even in just expressing that, we've already mentioned two disjoint sets. So the intersection of the complement of A and complement of B and the union of A and B are disjoint, and their union is the sample space, right? So the sample space is the union of A union B, because A union B would cover, should have done a different color, A union B would cover all the points inside here, and then what's outside, well, that's the complement of A intersection with the complement of B. Okay, so we got two disjoint sets, so then by axiom 3, the probability of their union must equal the sum of the individual probabilities so we know that the probability of the sample space is 1, so I'm just going to put the 1 there. Okay, and then what else do we know? Well, we know how to get from the A union B to A intersection B, and that seems like it would be promising here. So let's remind ourselves how we do that. Probability of A union B, you'll recall we've shown that it's equal to probability of A plus the probability of B minus the probability of A intersection B. Okay, so then let's just replace this expression here, and what do we get? We get that 1 is equal to the probability of the complement of A intersection of the complement of B plus the probability of A plus probability of B minus probability of the intersection of A and B. But what is that? It's just probability of A times probability of B. Okay, and now we can isolate this term to a term of interest to one side, so we would get that the probability of complement of A intersection of the complement of B is equal to 1 minus the probability of A minus the probability of B plus the product of the probability of A and probability of B. And there's a little algebra to do here. We got 1 minus probability of A, then we can factor minus probability of B here, and we get 1 minus probability of A. Okay, and there's a little bit more algebra to do here, and I just need a little bit more space. So I'll write this over here. So now we can factor out 1 minus the probability of A, and then what we get is 1 for this part minus the probability of B, and we know that 1 minus probability of A is the probability of the complement of A, and we know that 1 minus probability of B is the probability of the complement of B, and we got to the expression that we were trying to get to. Okay, so that proves this part as well. And this was, I apologize, this was part C. And the last thing I wanted to cover is this concept of mutual independence. When do we say that three events are mutually independent? or when do we say that a collection of n events is mutually independent? So we say that events a1 through an are mutually independent if for any subcollection we have that the probability of the intersection of these events is equal to the product of the individual probabilities. So let's look at that in somewhat more detail. So this is what we're trying to focus on, what it means for events to be mutually independent. But first, let's look at pairwise disjointedness and mutual disjointedness. It's no surprise that the authors have never defined mutual disjointedness, and that is because pairwise disjointedness implies mutual disjointedness. So an example will help clarify that. So if we have three events A, B, and C, pairwise disjoint means that any pair we pick, A and B, those are disjoint. A and C, those two must also be disjoint, and B and C, those two must also be disjoint. So pairwise disjoint just means every pair is disjoint. But notice that if every pair is disjoint, then necessarily that implies that the three of them, A, B, and C, cannot have any points in common. So pairwise disjointedness and mutual disjointedness, they refer to the same thing. In fact, pairwise disjointedness implies mutual disjointedness. But this is not the case with independence. Let's take a look at an example where we have three sets and what it would mean for them to be pairwise independent, and then what it would mean for them to be mutually independent, and we'll look at four sets and what it would mean for those to be pairwise and mutually independent in turn. So if sets A, B, and C are pairwise independent, that means that every pair of them is independent. So A and B must be independent, and we know what that means. That means the probability of their intersection must factor this way. Same for A and C, B and C, right? So, and those are all the pairs we conform with three sets. But mutual independence requires that for any collection of events that this factorization of the intersection of the sets holds. So in addition to the three conditions we just saw from pairwise independence, mutual independence in addition requires that the probability of the intersection of the three of them also factors. And the authors have some very nice examples. They have one example in which this fourth condition holds, but not the other three. And so those are not mutually independent. They have another example in which the first three hold, but not the fourth one. And then, you know, I also flush it out here for four sets, just to be clear in the distinction between what it would mean for four sets to be pairwise independent and mutually independent. You see, in pairwise independence, we just pick all the possible pairs, and the intersection of these must factor. But in mutual independence, in addition to those six conditions, we now have the intersection of three sets, and there are four such sets of three, and then additionally the intersection of all four sets must also factor this way. So just be careful and make sure you distinguish between pairwise independence and mutual independence. We don't need to worry about that when it comes to disjointedness, because pairwise disjointedness implies mutual disjointedness. And that's it for this section. I'll see you in the next one.